Hey everyone, so in this video we're going to look at derivatives as velocity and other rates of change. So far we've looked at derivatives in terms of non-applied equations. We've been given the original function in function notation, f of x, or in terms of y, both meaning the same thing. If we were to take the derivative of each of these, we would get the notation f prime of x or df dx, or for the y equation we would get y prime or dy dx, all meaning the same thing, the first derivative. If we were to take the second derivative, we would get f double prime of x or y double prime, or if you choose to use dy dx notation, it would be d squared f dx squared or d squared y dx squared, all meaning the second derivative. So we have our original equation, followed by the first derivative, followed by the second derivative. So how does this relate to the real world? Remember that derivative means slope or rate of change. So in the real world, we have our original function f of x or y, but in application problems this is called s of t, meaning position. So the y value gives us a position. So when we take the derivative, we get f prime or dy dx. Remember, derivative is slope or rate of change. F prime will be the rate at which position is changing, also known as velocity. So our first derivative is velocity. And our second derivative would be the rate at which velocity is changing. So how fast is the speed changing, which is known as the acceleration. So the derivative of position would be velocity. How fast is our position changing? The derivative of velocity would be acceleration. How fast is the velocity changing? Let's take a look at an example. An object shot upward. So let's say we have this object, and this object is shot directly upward. Assuming it's perfect, it should come right back down after a little bit thanks to gravity. Knowing the path that this object must take, we know it must go upward, having a positive velocity. And then at some point, it will come back down, having a negative velocity. So that point between where the object is going up to where it's going down, it changes from a positive velocity to a negative velocity. On any number line, we can see the change from positive to negative, or vice versa, negative to positive, would have a certain value in the middle. That value would be 0. So that point at which it changes from going up to going down is where the velocity would be 0. So an application of this would be a dynamite blast propels a heavy rock straight up with a launch velocity of 220 feet per second. It reaches a height of s equals 220t minus 11t squared after t seconds. The important information here is this equation. It is telling us our position at any time t seconds, because position would be our height. From this problem, we might be asked, when does the rock reach its highest point? The rock reaches its highest point once it's done going up, at which point it starts to come back down. So the rock reaches its highest point between a positive velocity and a negative velocity. And remember, that point between positive and negative is the number 0. So we want to find when the velocity is 0. In order to do this, we must first find the velocity. Remember, velocity is the derivative of the position function. So using the power rule, we take the derivative of the position function and get 220 minus 22t as our velocity. Again, we want to find when the velocity is 0, so we're going to set velocity equal to 0 to find the value of t. When we solve for t, we get 10 seconds. I know it's seconds because in the problem it says after t seconds. So what does this represent? Well, it represents when the velocity is 0 or when the rock reaches its highest point. Another question we might be asked is, how high does the rock go? In the last problem, we found when the rock reaches its highest point, and that is the point between when the velocity is positive and when the velocity is negative. So we got a time of t equals 10 seconds, which again is the point where the velocity reaches 0 because it goes from positive velocity to a negative velocity. But we're not trying to find the time when the velocity is 0, we're trying to find how high the rock goes, or in other words, the position. So we are given a position function based on the time t. Given that we know that it reaches its highest point at 10 seconds, we can use that, substitute 10 seconds in for t in the position function s, and I get 1100. And if I look back at the problem, I can find a distance unit right here. Feet per second is my velocity, so that means the position is in terms of feet. So because the rock reaches its highest point at 10 seconds, its height at 10 seconds would be 1100 feet. Yet another question we might encounter with this type of problem is, what is the velocity when the rock is 704 feet above ground, and what is the rock doing at that time? Now I can see that the question is asking me to find a velocity, and looking at my velocity formula, I have a formula that is in terms of time. I don't have the time currently, I only have the position. So going back to my position function, I can see that by giving a position, I will be able to find the other missing variable for time. So this is going to be a two-step problem. First, before we can even find the velocity, we need to know what time the rock reaches a velocity of 704 feet above ground. And once we know the time, we can then use the velocity formula to find the rock's velocity. So I take my given position and substitute in for position in the function of s. Now at this point, some algebraic strategies should come in. Seeing that we have 3 terms and the highest exponent is a quadratic, means that you should get all your terms to one side first. So if we subtract the 704 to the right side, and notice that I've reordered my terms so that the quadratic term comes first, followed by the linear, then the constant term. This makes it easier for when I use the factoring method or the quadratic formula. At this point, you should either set up for factoring or set up for using the quadratic formula. I know that this factors nicely, so I'm going to go ahead and do that. But if you were to use the quadratic formula, your a value would be negative 11, b would be 220, and c would be negative 704. If I factor out a negative 11, I get a trinomial that factors nicely into t minus 16 and t minus 4, which means that I get 2 solutions, t equals 16 seconds and t equals 4 seconds. Now before we move on, let's talk a little bit about why we got 2 different times when the rock reaches a height of 704 feet above the ground. Last problem, we learned that it reached a height of 1100 feet. So in the time before and after that, it must have reached less than that, or somewhere around 704 feet at some point in time on the way up and also on the way down. So one of these, we can probably guess which, is the time at which it's going up to reach its highest point, and the other is the time at which it's going down. And what's really neat is that our velocity will show that. So the second step, now that we've found the time at which our rock reaches a height of 704, we're going to take both of those times and plug them into the velocity formula for t, because they're the time, and we're going to figure out what the velocity is. So the velocity at time t equals 16 is negative 132, and the velocity at time t equals 4 is positive 132, and I can get my units by looking back at the original problem and seeing that the height is in terms of feet and the time is in terms of seconds, so my velocity is feet per second. And last but not least, we need to answer the question, what is the rock doing at that time? Well, at time t equals 16, we know that it's at 704 feet above the ground, but where is it going? By looking at the velocity, we see we have a negative number. Remember, velocity is the rate at which distance changes, or your speed. And if we have a negative speed, that means our object is going down. So at 16 seconds, our rock, is going downwards. And at 4 seconds, we have a positive velocity of 132 feet per second. So because the velocity is positive, our object is going up. So to recap, if we are given a height of an object and we're trying to find the velocity of the object, first we need to know what time the object reaches that height. Once we find that, we can plug that time into our velocity equation and figure out what the exact velocity is. And based on the sign of the velocity, positive or negative, we know in which direction our object is going. Yet another question we might be asked about a problem like this is, what is the acceleration of the rock at any time during its flight? Let's take a few steps back. We started with the position function, and the derivative of the position function is equal to the velocity, because velocity is how fast position changes. And we found the velocity equation to be 220 minus 22t. And if acceleration is how fast velocity is changing, then the acceleration would be the derivative of velocity. And you can also think of it as the second derivative of position. So we find our acceleration by taking the derivative of the velocity equation using the power rule. 220 will cancel out because it's a constant, and the derivative of negative 22t is just negative 22. So that means our rock is falling at a rate of negative 22 feet per second squared due to gravity. So again, acceleration is the first derivative of velocity or the second derivative of position. If you start with position, you must take your derivative twice in order to get acceleration. If you start with velocity, you must take your derivative once in order to get acceleration. One last question we might get from this type of problem is, when does the rock land? Most people's first instinct is to say it lands when the velocity is 0 because it's hit the ground, it's stopped. However, this doesn't work for several reasons. We learned in the first problem we did that the velocity equals 0 when it reaches its highest point, not when it reaches the ground. We can also consider the parabola represented by position. This graph will actually continue forever towards negative infinity in the y, so it'll look something like this. But we know the rock starts on the ground, gets projected upwards, and then comes back down and lands on the ground. So our equation does not account for the ground, which means that this equation only works for a specific time period, from when the rock leaves the ground to when the rock comes back to the ground. So we know that the rock doesn't reach the ground when velocity is 0. So we must know something else. And we do know that on the ground, the height of the rock is 0. So there's actually no calculus being done here, only algebra. To find when the rock reaches the ground, we're going to find when the height is 0. So substitute 0 in for the position in the function 220t minus 11t squared, and now we have a two-term quadratic equation. We could solve this by using the quadratic formula or by factoring. I noticed that both terms have a common factor of 11t. So when I factor that GCF out, I get this term left over. By setting each piece equal to 0, I get t equals 0 and t equals 20. And by intuition, we can say that t equals 0 is when the rock leaves the ground, and t equals 20 must be when it comes back to the ground, which makes sense. Because if we have a rock and no extra resistance or force whatsoever that gets shot up into the air, and from part A we learned that it reaches its highest point at 10 seconds, well, the rest of the journey must also take 10 seconds, so it should take the rock 20 seconds to reach its highest point.